Biotechnological innovations have combined to make artificial limbs much more comfortable, efficient, and lifelike than earlier versions. Future innovations are likely to depend on the interaction between amputees' demands, advances in surgery and engineering, and sufficient healthcare funding to sustain development and application of technological solutions. Prosthetics can be made for people born without limbs. Prosthetics can also be made for people who are involved in an injury or develop diseases that result in the loss of a limb. Therefore, limbs can be made in many shapes and sizes for children and adults. The components of a prosthetic consist of a fitter socket, a pylon, cuffs and belts that attach to the body, and socks that cushion the area of contact on the limb. Materials that can be used to make prosthetics include plastic, such as copolyester, and materials like titanium and aluminium due to being lightweight. Carbon fibre is also used. Over time, the materials used have changed. For example, wood, steel, and rubber were used for different components of prosthetics in previous years, but are no longer used due to being heavy. Before starting this project, I knew prosthetics could be made in a do-it-yourself fashion through 3D printing. Scanners can be bought to create a fitting socket for a prosthetic. However, not everyone can afford a device that would be capable of using a scanner. Other ways prosthetics can be made is through artificial intelligence, machine learning, ultrasound technology, and the electrode approach. Bionic limbs can now be made where, for example, the thumb can grip things. These days, amputees can design prosthetics to look how they want them to look. Leading on from this, my fact question for this 20% time project is how are prosthetics currently evolving due to biotechnological advancements? To find this out, I looked at a few areas that could affect particular growth and development of prosthetics. First, I looked into what the amputees' demands are. I researched this to hopefully learn how the biotechnological industry is creating advancements and evolving based on their customers. Then I looked into what the effect of price is on the advancements of prosthetics. This will show if advancements are being limited due to the price companies are selling their prosthetics for. Next, I found out what advances are occurring in surgery and engineering. This information will provide a deeper insight into whether prosthetics are being limited due to physical surgery or engineering properties. Finally, I looked at whether healthcare has sufficient funding to sustain development and application of technological solution. This will hopefully provide a deeper insight into whether prosthetics are being limited due to monetary problems. So let's start with question 1. What are the amputees' demands? Today, otherwise healthy individuals with amputations want to be able to participate in a full range of normal responsibilities. For example, walk without a limp and engage in recreational and sporting activities. This demand has allowed for many prosthetics to be made to allow an amputee to live a near to normal life without having to worry about engaging in particular activities. Another want that amputees have expressed is that they want a realistic limb, something that is lifelike. The present state-of-the-art prosthetic has been made due to this demand. It is the creation of a carefully sculpted silicone match for the opposite limb, with individual colouring to give a lifelike finish. Therefore, amputee demand for more versatile, high-performance prosthetics with more lifelike external coverings will fuel further innovations. The next question we will address is what is the effect of price on the advancement of prosthetics? The market for low-cost, limited-functioning devices will continue to expand in an effort to meet the needs of the developing world as well as the funding restrictions that are increasingly common in all economies. Lower manufacturing costs with particular limbs may permit their use in developing countries, where the cost of more complex technology is prohibitive. Initially, prosthetic innovations are used mainly by amputees with private funding, particularly those who are competitive athletes. As experience is gained, manufacturers discover how to apply the same principles to moderate cost devices intended for less active individuals. Modern industrial fabrication can create lightweight, low-cost components with sufficient functioning for limited walking. This might be sufficient for today's typical elderly amputee. Some designs may also be made moisture resistant and therefore suitable for use in the shower or on the beach. As spoken about previously, the lifelike silicone prosthetics that have been made to create a more realistic limb unfortunately are custom-made skins that cost about $3,500. Since they need replacement after a few years because of unavoidable wear and tear from normal use, this is very expensive to have to regularly replace. Because of the costs involved, most amputees currently receive semi-custom external coverings that are mass-produced from less expensive materials and provide only a generic external experience. Therefore, from this research, we can conclude that advancements are not entirely being limited due to the price companies are selling their prosthetics for. Instead, high manufacturing costs and variable insurance coverage serve as barriers to prosthetic access. These factors are magnified in many developing countries, especially when knowledge and access to prosthetic technologies is not universal. Moving on to our third question, what advances are occurring in surgery and engineering? Innovative technologies are being adapted from the aerospace and computer industries and being applied to high-performance artificial limbs. Advances in surgery and engineering have allowed for innovations to be made where the amputee can control their artificial limbs through their nerves. Examples of this in the upper extremity include myoelectric prosthetics, which harness the EMG signals of the residual limb muscles to trigger the function of a robotic prosthetic arm or hand. Myoelectric signals are captured through surface electrodes on the skin. Another example includes centrally controlled prosthetics, which operate via cortical inputs that allow for the operation of a prosthetic arm. This means a prosthetic can be controlled by a brain-computer interface. A brain-computer interface is an alternate method to record and interpret the communication between the CNS and the pathways of the peripheral nervous system. TMR is a surgical procedure that involves reconnecting transected nerves to remaining muscles within the residual limb or chest. By doing so, each newly innervated muscle is able to generate a unique myoelectric signal, thereby increasing the overall number of sites of control and enhancing prosthetic function. Examples of how surgery and engineering have driven lower limb innovations include microprocessor-controlled knees, which use computer chips to interpret signals from an accelerator that is embedded within the leg to provide variable resistance to knee motion. Another example is newly available powered lower limbs that incorporate motors. These artificial muscles produce force and movement within the limb to replace lost muscles and restore a more normal function. This information has provided me with the conclusion that physical surgery and engineering properties are increasing innovation and advancements in regards to prosthetics. While many may not have access to these new prosthetic advancements, much remains to be done with regard to the development, evaluation, and distribution of bioelectric prosthetics due to technological advances and surgical innovations. Our final question is, does healthcare have sufficient funding to sustain development and application of technological solution? Future use of new prosthetic components is liable to be controlled by funding constraints in both developed and developing countries. The International Committee of the Red Cross has established an initiative to produce low-cost plastic prosthetics made by unskilled local workers for areas where conflict or environmental catastrophes have resulted in large numbers of traumatic amputations. The U.S. Army Medical Research and Material Command, the Wounded, the Department of Defense, and Defense Medical Research and Development Program support and fund research as well as others. In conclusion, before participating in this 20% time project, I was drawn to discover more about this topic and how prosthetics could be advanced due to a few reasons. About 185,000 amputations are performed in the United States each year. 2 million people in the United States are living with limb loss, and 2,000 babies in the United States are born each year without an upper or lower limb. Prosthetic rejection in children is also quite regular and causes children to abandon their prosthetics. The cost of a prosthetic can range from $5,000 to $50,000, and their lifetime is around 3 to 5 years. The waiting list for a printed prosthetic arm is around 18 months long. From this project, I have learned how prosthetics are currently evolving due to biotechnological advancements. One massive development has been seen in the interface between the stump and the socket. The portion of the prosthetic that fits over the limb remnant, the socket, determines the amputee's comfort and ability to control the artificial limb. In recent years, researchers have developed a variety of thicker gel materials that add a measure of cushioning while retaining the benefits of the original liners. Another area of development can be seen in the shock-absorbing mechanisms that have been made to reduce impact forces. A growing number of prosthetic knees now include a stance flexion feature, which is designed to absorb shock and stimulate knee flexion, since amputees worldwide have begun to regularly run, jump, and jog. Finally, microprocessor-controlled movement offers symmetry in the swing phase and makes sure the knee will not buckle unintentionally during standing. This works by sensors in the ankle and shin continually assessing the position of the leg. Such technology, however, costs about 4 times as much as limbs with mechanical knee controls. Therefore, prosthetics are constantly evolving due to biotechnological advancements, and many problems that amputees struggle with are being fixed. The only problem is that these new innovative prosthetics are currently very expensive, and therefore are not available to all amputees.